Many natural gas reserves contain nitrogen in concentrations ranging to about 20%. To meet pipeline specifications, the nitrogen level must be reduced to below about 4%. A large majority of nitrogen removal facilities use cryogenic distillation, but such units are economical only for large capacity wells. For smaller reserves, pressure swing adsorption technology has economic benefits, especially because the feed mixtures are available at high pressures. It is desirable to use adsorbents in PSA units that are selective to nitrogen. For most known adsorbents, however, the adsorption selectivity favors methane due to its higher polarizability. One practical solution is to rely on diffusion selectivities by using microporous materials such as LTA4A zeolite and ETS4 that have constricted pore openings. Nitrogen is a pencil-shaped molecule whose cross-sectional dimension is 3.3 angstrom, significantly lower than that of methane. Within constricted pores, such as ETS4, the diffusivities of nitrogen are significantly higher compared to that of methane by about 2 or 3 orders of magnitude. In a recent paper, Wilkins, Sawada, and Rajendran report data on the unary isotherms and unary diffusivities for Barium-Exchanged Reduced Pore Zorite that is a potential candidate for kinetic separations of nitrogen-methane mixtures. The objective of this presentation is to examine the mixture separation characteristics of Barium-RPZ using the Maxwell-Stefan diffusion model. I demonstrate the occurrence of uphill transfer of nitrogen and transient overshoots during mixture uptake. The origins of the transient overshoots can be traced to thermodynamic coupling effects that emanate from slight sizable off-diagonal contributions of the matrix of thermodynamic correction factors. If thermodynamic coupling effects are ignored, the overshoots are not realized and the separations are a lot poorer. For background to the theory of the Maxwell-Stefan diffusion equations and the incorporation into modeling of transient uptakes and transient breakthroughs, see my presentations on these topics on my YouTube channel. Let's start the analysis of adsorption and diffusion in Barium-Exchanged Reduced Pore Zorite by considering the unary isotherm data as published in the paper by Wilkins. The experimental data at 3 different temperatures, 30 degrees centigrade, 50 degrees centigrade, and 70 degrees centigrade can be fitted for both components, nitrogen and methane, using the single site Langmuir model, where the Langmuir parameter B is temperature dependent. The fits are shown here, in which the loadings are plotted against the surface potential. The surface potential phi serves as a proxy for the spreading pressure, which for a unary system can be determined analytically if the unary isotherms are described by the single-site Langmuir model. The advantage of using the spreading pressure concept is discussed in detail in my presentation on this topic on my YouTube channel. In the context of unary isotherm data fitting, the entire data set can be fitted using three parameters: the saturation capacity, the Langmuir parameter B0, and the energy parameter related to the temperature dependence of the Langmuir parameter. This parameter E is identifiable as the isosteric heat of adsorption. These parameter values for nitrogen and methane are very, very close to the ones reported in this paper. But for the calculations I will be presenting in this presentation, I use these values as reported here. The advantage of using the surface potential as x-axis instead of the bulk fluid pressure or bulk fluid fugacity is that all data points at various temperatures collapse into a single curve that can be fitted quite easily using, say, the Excel solver. The description of the intra-crystalline diffusion of nitrogen and methane within the pores of Barium-RPZ are described by the Maxwell-Stefan diffusion formulation. For a binary mixture, the Maxwell-Stefan equations are written in this manner, in which we define a set of three diffusivities. D1 and D2 represent molecule wall interactions, and furthermore there is another diffusivity D12 that describes correlation effects. In other words, how the intra-pore hopping of one molecule influences the mobility of the partner molecule. For restricted pore structures such as barium ETS4, LTA4A Zorite, and Barium-RPZ, the first right member of these equations are not expected to be important. For further background, I refer you to my publications on this topic. The chemical potential gradients can be related to the gradients of the molar loadings Q1 and Q2, and the factor here, which is called the matrix of thermodynamic correction factors, can be determined from a description of mixture adsorption equilibrium, say the ideal adsorbed solution theory. An important and persuasive advantage of the use of the Maxwell-Stefan diffusion equations for describing diffusion inside microporous materials is that the Maxwell-Stefan diffusivities D1 and D2 that quantify molecule wall interactions in a binary mixture are the same as those for the corresponding unary systems. Therefore, in principle, the unary uptake experiments as reported in the paper by Wilkins, can be used to back out the Maxwell-Stefan diffusivity data. I show here an example of the uptake for methane, and the continuous solid lines drawn are the solution to the Maxwell-Stefan unary diffusion model, duly taking account of the thermodynamic correction factors. It is noteworthy that my model for unary uptakes do not separately account for surface barriers, as done in this article by Wilkins. Therefore, using the unary uptake data for methane and nitrogen, the required information on the Maxwell-Stefan diffusivities required to predict or calculate mixture adsorption and diffusion characteristics can be obtained. We simulate the transient uptake of a binary mixture of nitrogen and methane at partial pressures of 200 kilopascals and 800 kilopascals respectively, at a temperature of 273 degree Kelvin, within a spherical particle of Barium-RPZ. The Maxwell-Stefan diffusivities used in the simulations are specified here. These are the values that are obtained by fitting the unary uptake experiments reported by Wilkins. In this animation, we examine the development of the loadings of nitrogen, shown in red, and methane, shown in blue, as it penetrates within the pores of Barium-RPZ. These loadings correspond to the conditions at the external surface of the particle, that is in equilibrium with the bulk gas mixture. It's remarkable to note that the nitrogen loading experiences a sharp and steep overshoot in its component loading and as time progresses, the loadings within the particle reduce in value to reach the same concentrations within the particle as on the external surface. The key to kinetic separations is to terminate the diffusion process and the contact time such that the component loadings within the particle correspond to the conditions during the earlier transients, and this results in significantly higher amounts of nitrogen within the particle as compared to methane. This slide shows the animations of the development of the component loadings of nitrogen and methane within the particle using the Maxwell-Stefan model, in which the thermodynamic correction factors are ignored and the matrix of thermodynamic correction factors is taken to be the identity matrix. Let's have a look at the simulations. Red is nitrogen, blue is methane. These are the surface concentrations that are in equilibrium with the bulk gas. We observe that the nitrogen has already equilibrated far earlier than methane, and no overshoot is experienced. So the overshoot that was experienced and demonstrated in the previous slide is attributable to thermodynamic coupling effects that must be duly accounted for in simulating mixture uptake. If we ignore thermodynamic coupling effects, no overshoot of nitrogen is experienced. The two sets of simulations with and without thermodynamic coupling are summarized in this graph, in which the spatially averaged component uptakes are plotted against square root of the time. The continuous solid lines are the simulations in which thermodynamic coupling effects are duly accounted for, and the dashed lines are the simulations in which the thermodynamic correction factors are ignored. And we note there that if thermodynamic coupling factors are duly accounted for, there is a significant overshoot in the component uptake of nitrogen, and this overshoot is beneficial for the kinetic separation of nitrogen-methane mixtures. This information is plotted in composition space in this right-hand diagram. This is time t is 0 and this is time t is infinity. With thermodynamic coupling, the component loadings follow a curvilinear path to equilibrium, whereas without thermodynamic coupling, the attainment of equilibrium is monotonous. Put another way, the equilibration trajectory that is calculated using a model that duly accounts for thermodynamic coupling effects follows the scenic route. This is a signature of kinetic separations. Following the scenic route is a consequence of the transient overshoots. So overshoots and scenic routes are signatures of all kinetic separations. And these signify the occurrence of uphill transport of nitrogen, because we attain supra-equilibrium loadings during the early stages of the transient equilibration process. Having examined the intra-particle uptake of nitrogen and methane within Barium-RPZ, we now turn our attention to transient breakthroughs in a fixed bed adsorber. We consider a feed mixture at 273 degree Kelvin. The partial pressure of nitrogen in the feed mixture is 20 kilopascals, and the partial pressure of methane in the feed mixture is 80 kilopascals. The transient breakthrough simulations were performed, and the results are plotted in this graph, in which the dimensionless concentrations at the exit are plotted against a parameter in which t is the time in seconds, q0 is the volumetric flow rate at the inlet in units, say, of liters per second, and m sub ads is the mass of adsorbent in the bed. Methane elutes earlier than nitrogen because nitrogen is preferentially taken up within the pores due to diffusion selectivity, and during the initial time period, methane, meeting the pipeline specifications, can be recovered from the exit of the fixed bed. Let's have a look at the animation showing the development of the concentration profiles of methane, shown in blue, and nitrogen, shown in red, as they develop along the length of the fixed bed. Nitrogen being preferentially taken up within the pores moves along the bed in a slower than methane that is rejected into the gas phase, and methane elutes the bed earlier than nitrogen, and the pipeline specifications for methane can be realized. I summarize here the takeaways from this presentation. For nitrogen methane separations using Barium-RPZ, uphill transport of nitrogen is realized. From the uptake simulations, we've established that transient overshoots in the nitrogen uptake occurs, and the approach to equilibrium follows a serpentine trajectory in composition space. Overshoots and serpentine trajectories in composition space are signatures of kinetic separations. We still need to ask the question, can Barium-RPZ compete with Barium ETS4 for commercial use in natural gas purification? We shall address this question in a subsequent presentation.